Welcome back to part 2 of the momentum lesson by the physics teacher. In today's lesson, we are going to discuss the conservation of momentum, elastic collisions, and we are going to work out examples related to the elastic collisions. But first, let's look at the law of conservation of momentum. The law of conservation of momentum states that the total momentum before collision is equal to the total momentum after collision. Now, let's look at the following animations to understand better the law of conservation of momentum. I am going to ask you this question. What do you think will happen when the ruler is pulled backwards and then pushed towards the coin? Pause the video and think of an answer. Let's see. As you might have properly guessed, the momentum of the ruler was transferred to the coin, causing it to move forward. Assuming that no energy was lost, by the law of conservation of momentum, the momentum of the ruler before it collided with the coin is equal to the momentum of the coin after. Let's look at the example of a Newton's cradle. I am going to ask you the same question. Why do you think that when the first ball collides with the second ball, the last ball goes up? Pause the video and think of an answer. On collision, the momentum of the first ball is transferred from one ball to the other until it reaches the last one. The last ball has no other body in front of it to transfer the momentum, and therefore it goes up. Assuming that no energy was lost, the momentum of the first ball is equal to the momentum of the fifth and last ball. Now let's focus on the first type of collision, that is, elastic collisions. During elastic collisions, when one body moves and collides with another, the two bodies remain separate from each other. In the process, momentum is transferred from one body to the other. Elastic collisions have a general mathematical model that you can make use of when working out a question about elastic collisions. Let's look at this model and explain it step by step. The model consists of splitting the problem into the before and after. Then, the bodies in question are drawn, and the one moving have an arrow to indicate the direction of motion. Then, the respective value of mass and velocity for each body is written underneath each respective body. Take note that the mass does not change after collision, however, the velocity does change. Then, the conservation of momentum is written mathematically. Following this, ask yourself, how many bodies do I have before collision? In this case, you have 2, and therefore you write 2 brackets with the momentum equation for body A and 1 for body B. You ask the same question for the after part, and in this case you have 2 separate bodies, therefore you write 2 brackets with the momentum equation, 1 for body A and 1 for body B. The next step would then be to replace the symbols with the respective value, as you are going to see later on in this video when we are going to be working out some examples related to elastic collisions. This model shows you a situation where before collision there are 2 bodies moving in opposite direction. They collide and bounce back in opposite direction. As you can see, the velocity of the body moving backwards has a negative sign attached. This is very important because it makes a huge difference when it comes to the mathematical part. Now, to practice the law of conservation of momentum and elastic collisions, let's work out the following examples. Okay, so let's look at example number 1. In example number 1, we have a car of mass 2,700 kilograms was moving with a speed of 15 meters per second when it collided with a van of mass 3,200 kilograms, which was initially at rest. If after the collision the car came to a complete stop, find the final velocity of the van. So, when you read the question, you should be able to identify that you have 2 bodies, and when they collided, these 2 bodies remain separate from each other. As a result, that is a case of an elastic collision. Now, ideally, as mentioned, you start by splitting the situation in the before and the after. Before collision, we have two bodies, so I'm going to draw two rectangles to indicate that I have two separate bodies. One which belongs to the car and one which belongs to the van. The car has a mass of 2,700 kilograms, while the van has a mass of 3,200 kilograms. The velocity of the car before collision was 15 meters per second, while the van was initially at rest, which means that the velocity is 0. Then, after collision, we still have two separate bodies, so I'm going to draw two boxes again. Again, one for the car and one for the van. As mentioned in this video, after collision the mass remains the same, so the mass of the car is 2,700 kilograms, while that of the van is 3,200 kilograms. However, the velocity of both bodies change after collision, and the velocity of the car becomes 0 because it is stated that after collision the car came to a complete stop, while after collision the velocity moves with a particular velocity that we need to find. Then we move on to writing the mathematical representation of the law of conservation of momentum. So we write total momentum before collision equals total momentum after collision. Now, as mentioned before, you have to ask yourself, how many objects do I have before collision? In this case, you have two. So you're going to do two brackets with the momentum equation inside. One belongs to the car and one belongs to the van. Same thing, you ask yourself, how many objects do I have after collision? Again, you have two in this case. One of them is going to be for the car and one of them is going to be for the van. The next thing is now that you have to replace the symbol with the numbers. So the mass of the car is 2,700 kilograms and its velocity was 15 meters per second. The mass of the van is 3,200 and its velocity was 0. These two brackets, remember, they belong to the before collision. After collision, we know that the mass remains the same, so 2,700, but the velocity of the car after collision goes down to 0. The mass of the van remains the same, but the velocity we need to find. We work out each bracket now, each individual bracket, so 2,700 times 15 is equal to 40,500. 3,200 times 0, that is actually equal to 0 because anything times 0 is 0. Same thing here, 2,700 times 0 is equals to 0 because anything times 0 is 0 plus 3,200 V. We simplify this part, so we end up with 40,500 is equals to 3,200 V. Now we need to find the velocity of the van over there, so we need to make V subject of the formula, and to do that we have to remove the 3,200 from the V and we take it to the other side. From multiplication it ends up getting into a division. So we end up with 40,500 division by 3,200 equals V. You work that one out and you find that V is equal to 12.66 meters per second. that is to 2 decimal places. Okay, now let's look at example number 2. In example number 2, we have a billiard ball X of mass 1.2 kilograms was moving at a speed of 3 meters per second when it collided with another billiard ball Y having the same mass but moving in the opposite direction with a velocity of 2 meters per second. After collision, the balls continued to move separately. On collision, the billiard balls bounced back in opposite direction, and if billiard ball X moved back with a speed of 1 meters per second, find the speed of the billiard ball Y after the collision. So, again, you have to identify that you have a case of elastic collision. Why? Because you have two separate bodies before collision, they collided with each other, but after collision, these two bodies remain separate from each other. So, similarly to example number 1, ideally we start with the before and after. Now, before collision, we have two billiard balls, so I'm going to draw them over here. One is X and one is Y. The mass of billiard ball X is 1.2 kilograms, and the mass of billiard ball Y is also 1.2 kilograms. The velocity of billiard ball X is 3 meters per second, and the velocity of billiard ball Y is negative 2 meters per second. The reason why I'm going to do negative 2 is because in the question, it is clearly stated that billiard ball Y having the same mass but moving in the opposite direction. So to indicate that billiard ball Y is moving in the opposite direction, you have to do a negative sign in front of its value of velocity, because remember, velocity is a vector quantity. Now, after collision, we also have the two separate billiard balls, so X and Y. We know that after a collision, the mass remains the same, but the velocity changes. Now, billiard ball X, after collision, it bounced back, so it's going in the backward direction with a velocity of 1 meters per second. So that's going to be negative 1 meters per second, while the velocity of billiard ball Y in the forward direction, we have to find that value. Similarly to example number 1, ideally we start by writing the mathematical representation of the law of conservation of momentum. Therefore, the total momentum before collision is equal to the total momentum after collision. And just like we did in example number 1, you have to ask yourself, how many bodies do I have before collision? In this case, you have 2. So you're going to have 2 brackets with the momentum equation inside. One belongs to the body X and one belongs to the body Y. Same thing after collision, you still have 2 bodies. Therefore, you're going to have 2 brackets, one belonging to body X and one belonging to body Y. The next thing that we need to do now is to replace the symbols with the numbers, with their respective value. So the mass of body X is 1.2 kilograms, while its velocity before collision was 3. The mass of body Y before collision was 1.2 kilograms, and its velocity was negative 2. The mass after collision remains the same, so the mass of X after collision is 1.2, but its velocity is now minus 1, and the mass of body Y is 1.2, and the velocity we need to find. We work out each individual bracket, and we get 1.2 times 3 is equal to 3.6 plus, I'm going to leave this in a bracket, you're going to see why really soon, 1.2 times negative 2, that is actually negative 2.4, 1.2 times negative 1, that is negative 1.2, and 1.2 times v, that is 1.2 v. Now, the reason I left the negative 2.4 in a bracket, because from your mathematics lesson, you know that a plus and a minus becomes a minus. So that is actually 3.6 minus 2.4, and over here we have negative 1.2 plus 1.2 v. We work this side first, so 3.6 minus 2.4, and we get a value of 1.2, and over here we end up with negative 1.2 plus 1.2v. We remove this negative 1.2 from this side and we take it over here, so from negative it becomes positive, so over here we end up with 1.2 plus 1.2 is equal to 1.2v. What we did is we took this negative 1.2 on the other side. Okay, so we try to simplify the equation, we try to simplify both sides of the equation with the aim of making v subject of the formula. So now we know that 2.4 is equals to 1.2v. To make v subject of the formula, we have to remove the 1.2 and we take it to the other side, and from times it becomes division. So 2.4 division by 1.2 is equal to v. You work that one out and you end up with an answer of 2 meters per second. That is the value of the velocity with which billiard ball Y moves in the forward direction.
Thank you for watching the second lesson of momentum. Stay tuned for part 3, where we are going to be discussing inelastic collisions. Till then, stay safe.